morning, all of you. I am Dr. Veena Bharti, Assistant Professor at IT Department. Today, I am going to take a lecture on that is the topic is Knuth-Morris-Pratt algorithm. So, what is KMP matcher? This is basically the string matching problem. That is, in this case, we have given a string S, and the problem of string matching deal with finding whether a pattern P occur in the string S or not. And if P does occur, then it returns the position of S where P occurs. That means in this case, basically, this is the string. That means there is a given string, and in this string we have to find the pattern P in the given string. So that is the problem of KMP matcher, that is string matching algorithm. So first one approach is OMN approach. That means the running time for an algorithm is M of n. That means it takes the M into n time to execute or to find the pattern in the given string. So this is one of the most obvious approach towards string matching, and it would compare the first element of pattern to be searched P with the first element of string S in which to locate B. If the first element of pattern P matches with first element of string S, then compare the second element of P with second element of S. That means if this is a string and a string is, let's say, A, B, A, B, A, C, and if pattern is here A and C. So we have to compare this by using, first we have to take the pattern P and its string is A, and we have to compare this pattern with the string S and its first element is A. If they matches, then we have to move forward and we have to compare the second element of pattern P with second element of string S. Okay, so if it matches, then it's okay. That means this is the exact location of pattern. If it does not matches, then we have to move back and we have to again compare the second element of the string S, that is B, with first element of pattern. And if it is matches, then we have to move forward, because in this case it doesn't matches. So we have to move forward and we have to take the third element of our string and first element of our pattern. So in this way, this is the naive approach to compare or to find the exact location of pattern P in a string S. So in this case, if this is the length of a string and this is the length of pattern, and if it is, its length is M and its length is N, then total time taken in this algorithm is total M into N. So that is why this approach is called OMN approach. That means it takes total of time O of M into N. So this is the basic approach, but KMP matcher approach is somewhat different. Okay, so this is the OMN approach. Here string S, this is A, B, C, A, B, A, B, C, A, B, A, C. This is the string given, okay, and this is the pattern. So here we have to compare P1 with S1, okay. If it matches, then we have to move forward. Again compare B with B. It matches, then we move forward. Then we have to compare A with C. If it matches, then we have to go forward. If it doesn't matches, then we have to go back and again compare the first element of pattern with the third element of string. So that is why it takes total M into N time. Okay. So after doing this procedure, that means after forwarding this procedure, we have detected the location of pattern at this location. That means the location would be 1, 2, 3, 4. That means at element S4. This is the location of our pattern where we have found the pattern in the string. Okay. So drawback of this approach. What is the drawback of this approach? Why we are taking another algorithm? Because if m is the length of pattern, okay, here this is the pattern, and if the length of pattern is m and n is the length of string, so this is string, and if its length is m, so this is certainly the matching time is of order O of m into n. This is very slow running time algorithm, because when we compare the element of S with which comparison had been performed earlier are involved again and again in comparison in some future iteration. For example, when mismatch is detected for first time in comparison of P3 with S3, as we have seen in this case here, when mismatch occur in P3 and S3, so here we have to again move back to this element. Okay, so that is the drawback of this. We have to return to directly to first position. So that is why it takes total O of m into n time. So that is the drawback. Okay. So here the first comparison that would take place between P0 equal to A, S1 equal to B. It should be noted that S1 equal to B had already been involved in comparison in step 2. So this is a repetitive use of S1 in another comparison. So that is why this is the drawback of our algorithm. So the second algorithm we are going to discuss is the Knuth-Morris-Pratt algorithm. So Knuth, Morris and Pratt, basically these are scientists that proposed a linear algorithm for the string matching problem, and the matching time is O of n. In previous case we have seen that the matching time is O of m into n, and in this case the matching time is O of n, that is linear time. That means by using KMP matcher algorithm, the total running time is reduced from m into n to O of n, that is in linear time we can make possible of comparing a string with our pattern. Okay. So here comparison with some element of pattern to be matched, that is the backtracking of string S never occur. Here backtracking doesn't occur, that is why it take total O of n time. So comparison of KMP algorithm. Here we have used the concept of prefix function. Prefix function, that is pi function we are using in this case, and the KMP matcher algorithm. So first we have to understood what is the concept of prefix function. Okay, so basically the prefix function pi for a pattern encapsulate knowledge about how the pattern matches against shift to of itself. That means in this case we haven't shifted directly to our first position, we have to shift according to our prefix function. Okay, so this information can be used to avoid useless shift of the pattern P. In other words, this enable avoid backtracking on the string S. So that is why the time is reduced, and the algorithm here is KMP matcher. KMP matcher algorithm, in this case we have to use the string function S, we have to use the pattern P, and the prefix function pi that we have to calculate as input and find the occurrence of P in S, that is our problem statement, and returns the number of shift of P after which the occurrence is found. Okay, so that is how KMP matcher works. So this is the algorithm of prefix function pi. Okay, this is the pseudo code to compute the prefix function pi. Here this is the example. If we have to compute the prefix function for any pattern P, so we have to follow this step. Okay, so here you see this is the pattern A B A B A C A. Okay, so in this algorithm initially we have to take m equal to length of P. So in this example length of P is 1 2 3 4 5 6 7. Okay, 7 is the length of this pattern. So initially we have to put m equal to length of P equal to 7. And the second step of this algorithm is we have to put the value of pi1 equal to 0. Okay, and k equal to 0. So here pi1 equal to 0 and k equal to 0. These are the initialization of algorithm. Okay, then next step. Here we have to do for q equal to 2 to m. Okay, this is the loop, and in this loop q equal to 2 to m means initial value of q is 2. Okay, so here we have taken the step 1, that is q equal to 2 and k equal to 0, that is its initial value. Okay, then we have to move forward while k is greater than 0. In this case we have seen that k equal to 0. So what we have to do? We have to do while k is greater than 0 and pk plus 1 is not equal to pq. This condition is not satisfied, so we have to go to if. So here if pk plus 1 equal to pq. So in this case pk plus 1. Okay, k equal to 0, that means pk plus 1 means k equal to 1, or we say pk plus 1 equal to, here pk plus 1 means here the value of pk plus 1 equal to a and q2. Here the value of q equal to 2, that means we have to compare p1 with p2 if they are equal. Since in this case these are not equal, so if pk plus 1 is not equal to pq, then qk equal to qk. Okay, and the value of qk is equal to 0, so initially k equal to k, and if it occurs, that means if it matches, then we have to perform this step, because in this case it doesn't matches, so we have to perform this statement, that means pq equal to k. So we have to put here pi2 equal to 0. According to our algorithm, pq equal to k, and pq equal to k means here q equal to 2 and k equal to 0. So we have to put pi of 2 equal to 0. Okay, so in this case we have put it the pi2 equal to 0 in our table, that is the prefix function. Okay, then we have to move forward. Okay, so now putting the value of q equal to 3 and k equal to 0, then we have to compare since here k equal to 0. So what we have to compare? K0 means k plus 1, that means 0 plus 1, p1 with p3. So after comparing p1 with p3, here these matches occur. So what we have to do? If pk plus 1 equal to pq, okay, then we have to set k equal to k plus 1. Okay, so here k equal to 0 and we have to set k equal to k plus 1, that means the value of k equal to 1, and pi q, that means the value of pi3 equal to k, that means we have to set the value of pi3 equal to 1. So in this case pi3 equal to 1 is set in this case. Okay, so here we have put it the value of pi3 equal to 1. Okay, now we have to move forward. We have to put q equal to 4. So we know that the value of k equal to 1. So what we have to do? We have to compare the value of q4 equal to qk plus 1. That means we have to compare the value of Q4 with Q2. Okay. So in this case, these matches occur. So what we have to do? If the matches occur, then we have to increment the value of K by 1. So K equal to 1, we have to increment it. So the value of K is set to 2. Okay. And the value of pi 4 equal to K. So the value of pi 4 is set is 2. Okay. So in this case, we have to set here pi 4, the value of pi 4 as 2. Okay. Then again, we have to move forward. Step 4, Q equal to 5, and here the value of K is incremented to 2. So now what we have to compare? We have to compare Q5 with Q3. Okay. If this matches, because we know that this again matches, so what we have to do? We have to increment the value of K by 1. So K equal to 2, we have to increment it. So value of K equal to 3 and pi Q. That means the value of pi 5 equal to 3. So in this case, we have found the value of pi 5 as 3. Okay. Then we have to move forward. Here Q equal to 6 and the value of K is set as 3. So what we have to compare? We have to compare Q6 with Q4. Okay. Now in this case, matches doesn't. Okay. It doesn't matches. So what we have to do? In this case, if it doesn't matches, then we have to directly put pi Q equal to K. So in this case, what we have to do? Here we have to compare because the value of K is set as 3. So in this case, this is this step do while K is greater than 0, because the value of K equal to 3 and pi K plus 1 doesn't match with PQ. So we have to set K equal to pi K. So in this case, the value of pi K here is, pi K means this value is 1. Okay. So what we have to do? We have to set again K equal to 1. Okay. Then if this doesn't matches, because we have seen that this is not equal to, so we doesn't go to if loop. We have to go to next step, that is pi Q equal to K. So the value of pi K means pi 6 equal to 1, because we have set the value of K as 1 according to this law. Okay. Then again we have to move forward and we have to go to Q equal to 7 and we have set K equal to 1. Okay. So that means we have to compare Q7 with Q2. Okay. This also doesn't matches. That means we have to go to this step. That means K is greater than 0 because the value of K is 1 and PK plus 1 doesn't matches with PQ. So we have to set K equal to pi K. Pi K means in this case the value of pi K, that is pi 1. So here the value is set as 1 in this case. So in this way we have to find the prefix function for any pattern. So this is the procedure we have to follow to compute the prefix function. Okay. Then the next algorithm is KMP matcher. Okay. So KMP matcher, in this case we have already discussed that we have to need 3 inputs. First is our pattern, second is our string, and third is the prefix function pi as input, and find a match of P in S. So this is the algorithm for KMP matcher. Here we have to set n equal to length of S, m equal to length of P, and we have to use the compute prefix function to compute the value of pi. Okay. And initially we have to set Q equal to 0 and loop for I equal to 1 to n. This is the loop we have to follow. So in this KMP matcher, this is the example for KMP matcher. Here, this is the string given and this is the pattern given. Okay. So in this case, we know that the length of a string is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So the value of n is equal to 15 and the value of m is equal to 7. Okay, and we have already computed the prefix function pi for this pattern. So this is the our prefix function, and what we have to do, we have to compare our string with our pattern. Okay, so initially size of s is 15 and the size of pattern is 7. So what we have to do, we have step 1, I equal to 1. I equal to 1. Here the loop is, we have to set q equal to 0 and the loop we have to follow is for I equal to 1 to n. So first we have to set the value of I as 1. Okay, so in this case I equal to 1 and q equal to 0. This is the initial value, and we have to compare. Here we have to compare, if q is greater than 0, pq plus 1 with si. Si means s1 with p1. Okay, so we have to compare p1 with s1. Here we have done comparison because they are not equal, so we have to move forward. Okay, since p1 doesn't matches with s1, p will shifted one position to the right. Okay, then in this case we have to compare s with p. So here this shift occurs and we have to compare p1 with s2. So step 2 is I equal to 2, k equal to q equal to 0. So we have to compare p1 with s2 if they matches. Okay, so in this case p1 matches with s2. Since there is a match, p is not shifted. Okay, so what we have to do, we have to set I equal to 3 and q equal to 1. So we have to compare p2 with s3. Okay, we have to compare p2 with s3, and in this case since it doesn't matches, so we have to backtrack on p and we have to again compare p1 with s3. Okay, so this is our backtrack. We have to compare p1 with s3. Now fourth step is to compare I4 with q equal to 0 because we have backtrack. So the value of q1 is again set to 0. Okay, so in this case we have to compare p1 with s4, and since matches occur, okay, p1 does not matches with s4. So comparing p1 with s5. Okay, since here this is the actually this is the value of s4 and this is the value of p1. Since it doesn't matches, so we have to shift from this to this position and we have to compare p1 with s5. Okay, since p1 matches with s5, so we have to move forward and we have to set I equal to 6 and q equal to 1. So comparing p2 with s6, since in this case p2 matches with s6, so we again move forward. This is our next step, and in this case I equal to 7 and q equal to 2. So we have to again compare p3 with s7. Okay, so p3 matches with s7, so we have to move forward, and the step 8 is I equal to 8 and q equal to 3. So we have to compare p4 with s8, and in this case p4 matches with s8, so move forward. I equal to 9 and q equal to 4. So here we have to compare p5 with s9. Okay, so in this case matches occur, so we have to move forward. I equal to 10, q equal to 5. Again we have to match our p6 with s10. Since in this case match doesn't occur, so that is the case. So what we have to do, p doesn't matches with s2, so we have to backtrack on p comparing p4 with s10, because after mismatch q equal to q5 pi5 equal to 3. So here what we have to do, here we have to see our pattern function. Okay, so in the pattern function, the value of pi5 equal to 3. So we doesn't have to backtrack to our initial value. We have to backtrack only to 3. So that is the advantage of our Knuth-Morris algorithm, because we doesn't have backtrack to our initial value. We have backtrack to the position, that is the prefix we have calculated earlier. Okay, so in this way we have again backtrack. Then we have seen that in this case we have to compare this, and here the step 11 is I equal to 11, and we have to match with it with Q4, because these patterns are already compared in our previous section. So we doesn't need to backtrack to P1, we have to backtrack to only 3. That means we have to backtrack to this position. Okay, so that is the basic advantage of our KMP matcher. So we have to compare P5 with S11. Okay, so in this case matches occur. Okay, so what we have to do, we have to match I12 with our Q5, and in this case also the comparing with P6 and S12. So P6 matches with S12. So next step is I equal to 13 and Q equal to 6. In this case also there is a when we have done a comparison, then matches occur. So what we have to do, we have find a pattern in this location. Okay, so this is the method for KMP matcher, and here pattern P has been found to completely occur in a string S, and the total number of shift that would takes place for matches to be found are I minus m, that is 6 shift are here. Okay, so that is the basic algorithm for our KMP matcher, and this is the running time analysis. In this case, the running time analysis, the compute prefix function, this is the compute prefix function, and this is the KMP matcher algorithm. So in this case, in the above pseudocode for computing the prefix function, the for loop, step 4 to 10, these run time is m time, and in this case total time is theta of n. So total time it takes is O of m plus n time. Okay, because O of m plus n time, so we can say that KMP matcher take total of O of n time to compare or to find the location of pattern at a string S. Okay, so this is the basic running time analysis of our KMP matcher algorithm. So that is why it would do better than our naive string matching algorithm. Thank you.